Ever wondered how multiple operating systems can run on a single machine? Well, that's where the concept of virtual machines comes into play. A virtual machine is essentially a software-based emulation of a computer system, allowing you to run multiple operating systems simultaneously on a single physical machine. Imagine having the power to operate Windows, Linux, and macOS, all on one device, without the need for separate hardware. It's a bit like having multiple computers packed into one. But how do these virtual machines come to life? That's where a special piece of software known as a hypervisor steps in. Acting as a kind of digital puppeteer, the hypervisor creates and manages these virtual machines. It cleverly abstracts the physical resources of your machine, that's your hardware, and carves out individual virtualized environments for each operating system to run in. It's the master of ceremonies, ensuring each guest operating system has its own virtual stage to perform on. To make things even more interesting, these guest operating systems don't have to be the same as the host operating system. That means you could be running Windows on your physical machine, but have a virtual machine humming away with Linux. It's like a digital melting pot of operating systems. So that's the basic idea behind virtual machines. But how does this all work? Stay tuned as we dive deeper into the fascinating world of virtual machines in the next segment. The magic behind virtual machines is the hypervisor. So what is a hypervisor? At its core, a hypervisor, also known as a virtual machine monitor, is a piece of software or firmware that creates and runs virtual machines. It's like a conductor leading an orchestra of virtual machines on a single physical hardware platform. Now, let's delve a bit deeper. There are two main types of hypervisors, aptly named Type 1 and Type 2. Type 1 hypervisors, also known as bare metal hypervisors, need no separate operating system to function. They run directly on the host machine's hardware. Imagine them as the foundation of a house, with each virtual machine being a separate floor built on top. Some examples of Type 1 hypervisors include the likes of VMware ESXi, Microsoft Hyper-V, and Xen. On the other hand, Type 2 hypervisors, also known as hosted hypervisors, operate on a conventional operating system. They are like an application running on your computer that can host other operating systems within it. Some examples of these include VMware Workstation, Oracle VirtualBox, and Parallels Desktop. One of the primary roles of a hypervisor is to abstract physical hardware resources. Think of it as a translator, converting the language of physical hardware into something that virtual machines can understand. This abstraction allows the hypervisor to provide a virtualized environment for the guest operating systems, enabling them to run as if they were on their own separate physical machine. So, in essence, a hypervisor is the bridge between the physical and the virtual, the tangible and the abstract. It allows us to create multiple, isolated environments on a single physical machine, where we can run different operating systems, all while managing the allocation of physical resources like memory, storage, and processing power. In the world of virtual machines, the hypervisor is the key player. It's the master of ceremonies, the orchestrator of this virtual symphony. It's what makes the magic of virtual machines possible. So, the hypervisor is the key player, but what about the operating systems that run on it? Each virtual machine runs its own guest operating system. This is a defining feature of virtual machines, and one that allows for exceptional flexibility. Guest operating systems are autonomous entities, independent from the host machine's operating system. What does this mean? Well, it means you could be running a Macintosh host machine, but your virtual machines could be operating on Windows, Linux, or any other operating system. This versatility is one of the key strengths of virtual machines, making them invaluable tools in various fields, from software development to cybersecurity. Let's delve a bit deeper. Each guest operating system believes it's operating on its own dedicated hardware. It's oblivious to the fact that it's running on a virtual machine and that there are potentially several other guest operating systems running on the same physical machine. This illusion is meticulously maintained by the hypervisor, which smartly manages the physical resources, allocating them to each virtual machine as needed. It's like a master puppeteer, carefully controlling each virtual machine while remaining unseen. The ability to run different operating systems on the same physical machine opens up a world of possibilities. It allows for software testing across different platforms without the need for multiple physical machines. It provides a safe environment to run potentially risky software without endangering the host machine. The autonomy of guest operating systems in a virtual environment is truly a game changer. But how does a guest operating system interact with the hardware? Let's explore that in the next scene. Virtual machines interact with hardware through virtual hardware. Imagine a theater where the actors are virtual machines and the stage is the physical hardware. The actors don't interact with the stage directly. Instead, they use props, our virtual hardware, to perform their roles. The props might be a fake sword or a wooden goblet, but to the actors, they serve the same purpose as the real thing. In the world of virtual machines, these props are the virtual CPUs, memory, storage, and network interfaces presented to each guest operating system. The hypervisor, our stage manager, orchestrates this performance. It ensures that each actor has the right props at the right time, managing the allocation of physical resources to the virtual machines. Just like a stage manager ensures that the actors don't bump into each other or disrupt the performance, the hypervisor ensures that each virtual machine operates independently, oblivious to the existence of others on the same stage. To the guest operating system, these virtual resources appear as real, tangible hardware. It can execute processes, store data, and send network packets, all without knowing that it's interacting with virtualized hardware. This abstraction allows us to run multiple operating systems, each with its own set of virtual hardware resources, on a single physical machine. So, we have multiple operating systems running independently, but what keeps them from interfering with each other? Virtualization provides a level of isolation and security. Now, let's delve into what that means. Virtualization is like a secure vault, a virtual fortress if you will, where each virtual machine operates in its own independent environment. It's like having your own private island in the vast sea of the digital world. This isolation is a key feature of virtualization technology. It ensures that each machine is kept separate from the others, creating a secure boundary that safeguards against interferences. Imagine you're running a mission-critical application on one virtual machine and a test application on another. Even if the test application crashes, it won't affect the mission-critical application. They're each in their own space, isolated from each other. Moreover, this isolation extends to the resources of each virtual machine. Each one has its own set of allocated resources, its own CPU, its own memory, its own storage. It's as if each virtual machine exists in its own bubble, oblivious to the others around it. This isolation isn't just about keeping things separate, it's also about security. It prevents one virtual machine from accessing or interfering with the resources of another. No unauthorized access, no meddling, no unwanted snooping around. It's like having a personal security guard for each virtual machine, ensuring that everything stays safe and secure. So virtual machines are isolated and secure. But how are resources managed? Let's explore that next. Hypervisors come with features for managing and allocating resources. When it comes to resource management, hypervisors are no slouch. They possess features like CPU scheduling, memory ballooning, storage provisioning, and network bandwidth control. CPU scheduling ensures that virtual machines get fair and efficient access to processing power. Memory ballooning helps to dynamically adjust the amount of RAM allocated to a virtual machine based on its current needs. Storage provisioning allows for the allocation and management of storage resources, while network bandwidth control ensures that each virtual machine gets its fair share of network resources. But the capabilities of hypervisors don't stop at resource management. They also have some nifty additional features up their sleeves. One such feature is the ability to take snapshots. This allows users to save the state of a virtual machine at a particular point in time, which can be incredibly useful for troubleshooting or for reverting back to a known good state. Another helpful feature is cloning. This enables users to create identical copies of a virtual machine. Whether you're testing a new software update or deploying multiple instances of an application, cloning can save you a lot of time and effort. Let's not forget about migration. Some hypervisors support live migration, which allows virtual machines to be moved from one physical host to another without causing any downtime. This feature is particularly beneficial for workload balancing, disaster recovery, or maintaining high availability in virtualized environments. And speaking of high availability, hypervisors can also help to ensure that your applications stay up and running. If a physical server fails, the hypervisor can automatically restart its virtual machines on another server. This can significantly reduce downtime and help to keep your services available to users. With all these features, virtual machines offer flexibility, scalability, and cost savings. They allow multiple workloads to run on a single physical machine, resulting in efficient resource utilization. Whether you're consolidating servers, developing software, deploying applications, or implementing a virtual desktop infrastructure, virtual machines can provide the versatility and efficiency you need. With all these features, virtual machines offer flexibility, scalability, and cost savings. So, that's a brief overview of virtual machines. We've delved into the fascinating world of hypervisors, guest operating systems, virtual hardware, and the crucial aspects of isolation and security. We've also touched on resource management and additional features like snapshots, cloning, migration, and high availability. Remember, virtual machines are indispensable in various scenarios, from server consolidation and software development to cloud computing and virtual desktop infrastructure. In the world of IT, virtual machines are indeed a game changer. They have revolutionized how we use hardware resources, making our computing environments more flexible, scalable, and efficient.